In this chapter, we are talking about tests of significance. This is where we are looking at whether or not the results that we have collected in a sample are statistically significant. So some of the things we're going to do are we're going to just talk about the reasoning behind a test of significance and why they work the way they do. We'll talk about specifically stating and interpreting hypotheses, which is what all of our tests are based on. And then we'll look at actually doing the tests and using p-values to do that. And we'll do specific tests for population means. So to get started, suppose that I claim that I make 75% of my basketball free throws. Okay. To test my claim, you ask me to shoot 20 free throws. Of those 20, I make only 7 of them. What would you say in response to this? Well, most likely you would say, I think you're full of it, right? Like, obviously 7 out of the 20 is not even close to 75% of the 20 free throws, right? 75% of that would be 15. Okay, and I got less than half of that. And so this is an example of where you've collected a sample, essentially, of 20 of my free throws and found that, I only made 7 of them, so it seems a little implausible that I actually do make 75% of my basketball free throws. And this is the whole idea behind testing things statistically. So to nail this idea down a little bit more, what we're going to be doing is saying when we look at our sampling distributions, which are normal, okay, then when we have a simple random sample, we'd like to know the likelihood that our outcome actually matches the expected outcome. Okay, in other words, if you think back to the basketball example, if I say that I make 75% of my free throws, okay, we'd like to know that after I do 20 free throws and I make 7 of them, what's the likelihood that I make 7 out of 20 if the claim is that I actually make 75%? Like, is that unlikely, or is it still plausible? Okay, so for example, making 75% of my basketball free throws, throwing 20 times, I would expect to make 15. But if I threw 14 instead, or 16, you wouldn't be that surprised. You'd say, well, that's not unlikely, right? Because obviously it's not going to be exactly 75%. Okay, so the question then is, well, the further away I get from that expected outcome, obviously the likelihood decreases, and that's kind of what we base our results off of. Let's look at an example of this and kind of quantify the question of how expected or unexpected a result is. Diet colas use artificial sweeteners to avoid sugar. These sweeteners gradually lose their sweetness over time. Trained testers sip a new cola along with drinks of standard sweetness and score the cola on a sweetness score of 1 to 10, with larger scores corresponding to a greater sweetness. The cola is then stored for a month at high temperature to imitate the effect of 4 months storage at room temperature. Each taster scores the cola again after storage. The sweetness loss scores for various colas are normally distributed with standard deviation sigma equals 1 and are given here, these numbers here. We'd like to know if these data are good evidence that the cola lost sweetness in storage. So a positive number, okay, indicates a loss of sweetness, and a negative actually means a gain, because these are sweetness loss scores. Okay, so what we want to do is say, well, suppose that the cola does not lose of sweetness. Okay, we would expect the average of these to be 0. Okay, we would expect a distribution that is normal, okay, with the standard deviation of 1, but we would expect that the sweetness loss is 0. Okay, I'm going to go ahead and draw that. So we have a normal curve, okay, and we've got our peak at 0. And we're going to go ahead and find the mean of this set of numbers. And I'm just going to do that in Excel. So here are my numbers, and I'm just going to go ahead and calculate my mean, or average for those numbers. Okay, so we get an average of 0.3. So the average here, x bar for this sample, is 0.3. Now, we have here a sample of 10 tasters, okay, sweetness loss scores. And so this distribution that we're looking at is actually going to be a sampling distribution where our sample size is 10. So this is a normal distribution with a mean of 0, and the standard deviation of this should be the sigma over the square root of the sample size. So 1 was the standard deviation divided by the square root of 10. Okay. So now, well, we got x bar equals 0.3. The idea is to know how far away from the expected mean is this. Okay. We know that for our sampling distribution, our expected mean is 0. And we're going to do this in terms of standard deviations. So we can compute the z-score for this sample mean. It is 0.3 minus the mean of 0 divided by this standard deviation of 1 over the square root of 10. So let's go ahead and compute that. We get equals 0.3 minus 0 and then over 1 over the square root of 10. All right, so this is 0.949 about, okay, 0.949. So this is less than 1 standard deviation away from the mean that's expected. So what that means then? So we're 1 standard deviation, which is right around here. Okay, is where we're at. And that doesn't seem super surprising, right? We know that from our 68, 95, 99.7 rule, we expect 68 of observations to be within 1 standard deviation, that which leaves 32% that's beyond that. And so it's not too surprising to end up with something that's, less than 1 standard deviation away. And so this doesn't seem to contradict the idea that there was no sweetness loss. So we would say that we did not find strong evidence that this cola lost sweetness over that month. Let's look at another example. We'll do a different cola, same idea. Okay, different cola, and we've got our 10 tasters, professional tasters, that have given a sweetness score. And we'd like to know if this is good evidence that this cola has lost sweetness. So again, we need to compute the mean. So in Excel, here we've got our numbers, and we'll go ahead and get our average for those 10 taste loss or sweetness loss scores, and we get 1.02. So x bar for this sample is 1.02, and we would like to know how far away this is from the expected mean. So again, if we have not lost any sweetness, okay, we would expect the average to be about 0. Okay, and so same idea. We've got a normal distribution with a peak at 0. Okay, we've got the same distribution, normal with a mean of 0, and the standard deviation is 1 over the square root of 10, since we've got a sample of size 10. And so we can compute the z-score for this mean that we found, 1.02 minus 0 over 1 over root 10. And we can go ahead and compute that in Excel as well. So equals the 1.02 over 1 over the square root of 10. Okay. We get 3.23 about. Okay. Now 3.23 standard deviations away from the mean. All right, so 1 standard deviation, 2 standard deviations, 3 standard deviations, and we're past that. We're out here. Okay, and we see that the likelihood of that happening is very small. Okay, and so that tells us that we have strong evidence that the assumption of a mean of 0, okay, the assumption that the cola didn't lose any sweetness, is a pretty weak, that's a weak assumption. And so we found strong evidence against that.